Signal flow graph is the next topic in control system. The name itself is very clear. It is a graphical representation of a system, and there will be a signal flow. There will be a signal flow from input to output. So that's why it is called a signal flow graph. So it is a graphical representation of linear equations, and any system, as we have discussed in the previous section, when a system is described by a block diagram and finding out the transfer function of a given block diagram or system is very complex. There are 9 to 10 rules we have already listed, and you must use the rules and find out the transfer function, and for each step you need to draw the reduced block diagram and finally get a single block to find out overall transfer function. Laborious, time consuming, complex, possibility of committing mistakes. Signal flow graph is not like that. It is a graphical representation of a system. It consists of only nodes and branches. For example, if you consider a block G, say this is R, this is C, output. As we have discussed in the block diagram, block represents functional description of that component. So C is equal to G times R. This is the output you get. C is equal to G times R. Now, in the case of signal flow graph, you will not find any blocks, any summing points. It has only arrows. So this same one you can represent as R, C with arrow G is the gain of that particular path. So output here also C is equal to G times R, but the advantage of this signal flow graph is there are no rules to find out the overall transfer function of the system, but there is a formula invented by S.J. Mason, and it is known as Mason's gain formula, invented by him. So you need to get some parameters which we are going to define now, substitute in the Mason's gain formula to get the overall transfer function. Remember that overall transfer function we may take for the analysis of stability or response, etc. So let us see what is signal flow graph, and when a block diagram is given, how to transform that given block diagram into signal flow graph, then how to apply Mason's gain formula to determine the overall gain or overall transfer function. Let us have one example or one linear equation that say it is y4 is equal to 3y1 minus 4y2 plus 5y3. This is a linear equation. Now I would like to represent this linear equation as a signal flow graph. It is possible. Y4 is a node, it is nothing but a variable, and y1 is also a node or input, it is a variable, y2 is also variable, y3 also variable. So I am joining now all these three to y4 with an arrow. Y4 is equal to 3y1, where 3 is the gain, y1 is the input. So y4 is equal to 3y1 minus 4y2 plus 5y3. So same equation is described in the form of signal flow graph. Where y4 is equal to 3y1 minus 4y2 plus 5y3. This way signal flow graph very easy to understand that what is given in the form of equation can be represented by a graph. So it is a graphical representation. Remember, it has only nodes, they are basically variables, and with arrows, branch, it is called as a branch connecting the nodes, and the number that is represented on the arrow is a gain of the system. If you take an electrical system, these nodes or variables are voltages and currents, whereas this 3, 4, 5, etc., it may be an impedance or admittance. So any electrical system or any system, as a matter of fact, it consists of variables as well as gains. So this is the representation of signal flow graph for this given linear equation. Before actually going into the block diagram, converting that into signal flow graph and finding the transfer function using Mason's gain formula, let us consider one example directly, the signal flow graph, and what are the parameters that we need to define in the Mason's gain formula we should come to know from this example. So let us see certain terms that are required to be defined for Mason's gain formula. Number 1 is forward path. What is meant by forward path? Forward path is the path connecting input and output nodes. Forward path is the path that is connecting input and output nodes. So you can see that in a signal flow graph, arrows are indicated that there is a signal flow. So see here 1, 2, 3, 4, 5 and 6 are nodes. 1 to 6, they are actually nodes. So node is a variable, and number of nodes that are present in this example are 6, and these nodes are connected by branches and whose gain is given, like between path 1 and 2 the gain is 1, here between 2 and 3 it is G1 and so on. So they are gains. So what is meant by forward path? Forward path is the path that is connecting input and output nodes. So here what is meant by input node? When I say node is a variable, it may be an input or output, then input node means the node which has only outgoing branches. Input node means the node which has only outgoing branches. So here the input node is only one, because there is only branches that are going out of that particular node. So input node is 1 here. Now next we need to define output node. Output node means it has only incoming branches. Output node means it has only incoming branches. You can see here 6 is the node, it has only incoming branch. So output node is 6. How do we know that it is an incoming branch? Because the signal is entering into the node 6, whereas here the signal arrow is indicated out of 1. That's why it has outgoing branch and this has incoming branch. So output node is 6. Now there is another node called mixed node. Mixed node means a node which has both incoming and outgoing branches. So if you take an example of 2 node, see that example of 2, it has incoming branch as well as it has outgoing branches also, and this is an incoming branch. So 2, 3, 4, 5 also. So all these are mixed nodes which has both incoming and outgoing branches. Now what is the definition of forward path? Forward path is the path connecting input and output. Forward path is the path that is connecting input node and output node, but no node should come more than once. So let me represent the path in terms of nodes, that is 1, 2, 3, 4, 5, 6. So, this is a forward path, I can say, connecting input and output nodes. So, 1, 2, 3, 4, 5, 6 is the path. Let me call this as P1 and what is its gain. So, as usual, like block diagram reduction rules, you need to get the gain of that path by multiplying all the gains. So, along this path, this is a forward path and its gain is product of these all gains of individual branches. So, it is G1, G2, G3. So, is there any other forward path? Let us identify. All this is required for Mason's gain formula to determine the overall transfer function. So, is there any second forward path? How many forward paths? As a matter of fact, how many forward paths exist in this particular example? This is one forward path already defined and the gain of that path is given as P1, G1, G2, G3. You can see now there is another forward path. It actually goes this way through G1, then it goes via G4 and through G3 and finally to the output. So, second forward path, this is forward path 1, forward path 2 is again starting from 1, 2, of course 3, but it is going via G4, 4, 5, 6 only, but what is its gain? Now, I will write as a P2, what is the product of that particular path gain? 1, G1, G4, G3 and 1. So, it is G1, G3, G4. So, second forward path identified in this example. So, you can see the difference, both are same nodes, but still no node is coming more than once in a particular path. That is the meaning of forward path. So, you can see now this 1, 2 via G5, it goes to the output. This is also another forward path. So, forward path 3 starts with 1 connecting input and output via 2, then it goes like this 5, then 6. So, the gain of that particular path is only G5, 1 into G5 into 1, so it is only G5. So, in this way you should identify how many forward paths that are existing in the given signal flow graph. So, 3 forward paths exist. Now, what other information we can find out from this? We need to find out, the second one is number of loops, number of individual loops. So, that is represented by L1, L2, L3, etc. L stands for loop. So, what is meant by loop? Loop is a closed path. It starts from a node and again terminates at the same node, but no node should come more than once. So, if you see here, I can say that what are the loops? Let us identify the number of loops. So, loop 1, you can see this 3, 4, 3. This arrow, it is going this way, then it is coming back. So, it is a closed path connecting 3 and 4 and coming back. So, 3, 4, 3 is the path of the closed loop 1, whose gain is product of this G2 and H1, product of G2 and H1. Now, you can see the second loop. You should identify, it is only an observation. See that, is there any other loop? Now, you can see this 3, 4, 3 again, but through this path G4 H1 is also a loop. Path is again same 3 4 3, but even one branch is deferred, we should represent it. But only thing is, no node should come more than once, and wherever you have started, you should come back to the same node. That is called a loop. So G4 H1. G4 H1 is another loop gain, and this way you need to identify any other loops are there. Loop 3. Loop 3, I am writing starting from 2, 3, 4, 5 and then back to 2. 2, 3, 4, 5 and back to 2, whose gain is L3, product of G1, G2, G3 and H2. That is the loop gain. So G1, G2, G3, H2. Next, is there any other loop you need to identify? Now you can see that from here again it starts another loop. I am trying to represent its gain. First loop path, then what is its gain? It is a product. So again you start from G1, 2, G4, G3 and H2. This is also another loop. So I start again from 2, 3, again via this 4, 5 and 2. Path looks same, but there is one branch that is differed from the previous loop. So what is its gain? Gain of that particular loop is product of G1, G4, G3, H2. So G1, G3, G4, H2 is the gain of this particular loop. You can still identify another loop in this system. Loop 5 is, it starts from 2 via G5 and it goes via H2 like this. So the path is 2, 5 and 2. 2, 5, 2 is the another loop that is identified here, and whose gain is product of G5 and H2. It is represented by L5 and the gain is given by G5 times H2. So this many loops exist in this system. This also required for Mason's gain formula. One is identifying the forward paths, and the second one is number of loops and what is the gain respectively you need to find out. Another information required for Mason's gain formula is number 3, pair of non-touching loops. Is there any pair? Is there any pair of non-touch loops? So what does it mean? Non-touch loop means loops which does not have a common node. It is said to be non-touch loops. For example, from figure itself it is very clear that this 3, 4, 3 G2 H1, if you see what is the node numbers 3, 4, 3, and if you see this 2, 5, 2 is not touching with 3, 4, 3. Non-touch means no node should come more than once, no node should repeat in the respective loops, then we say that it is a pair of non-touch loop. So this 3, 4, 3 is the loop, it is not touching this 2, 5, 2. You can see that this is the loop and this is the loop. That pair called non-touch loop pair. So I can say here L1 is this one G2 H1, and then it is not touching with this 2, 5, 2, that is L5. So this is one pair. I have identified that L1 and L5 pair is non-touch loop. So I need product of such non-touch loops pair. So L1 and L5 is one pair, second pair is L2 and L5. You can see L2 and L5 also they don't have common nodes. Even one common node is there, we cannot call it as a non-touch loop pair. So 3, 4, 3, 2, 5, 2. So this is again pair of non-touch loop. Pair of non-touch loop. So this is the information. One is number of forward paths, what is its gain, number of loops, what is its gain, then what are the loops which are not touching a pair. This is also required for Mason's gain formula. And in a particular problem, in a complex problem, we may have to see even is there any 3 non-touch loop pair. Not pair, but 3 loops which are non-touching. So that also we should have an information. Here what is meant by L2 and L5? There are 2 loops which are not touching, so I called it as a pair. But you may have to see in a problem if it exists 3 such loops which are not touching each other. Now let us see what is Mason's gain formula. So as I was mentioning that signal flow graph is a graphical representation and it consists of only nodes and branches. Nodes are variables and the gain of the branch is represented on the top of the arrow. So Mason's gain formula is a formula that is required to find out the overall transfer function of the system. So for that some information is required from the signal flow graph. Is you need to identify how many forward paths exist, P1, P2, P3 we have seen, connecting input and output nodes. Next, the number of individual loops and what is its gain. So loop is nothing but a closed path started from a node and terminates at a same node by not repeating any other node. So loop is a closed path and such loops are 5 in this particular example. This is also required for Mason's gain formula. And you need to identify further, are there any pair of non-touch loops? Are there any 3 such non-touch loops exist in the given system? So it is only an observation. You are not reducing the block diagram kind of thing and you are not using any such 9 to 10 rules here. It's only an observation, forward paths, loops and pair of non-touch loops you need to identify. Now what is the formula? The Mason's gain formula is meant for to determine the overall gain of the system or overall transfer function of the system. So it is given by T or T of S is nothing but C of S by R of S. One by delta sigma P K into delta K. This is the formula where sigma K equal to 1 to N, that gives how many forward paths exist in the system here. So 1, 2 and 3. So sigma K equal to 1 to 3. Now I can rewrite this as 1 by delta into P1 delta 1 plus P2 delta 2 plus P3 delta 3, where P1, P2, P3 is the gain of respective forward paths that we have already observed. What is delta? Delta is 1 minus sum of individual loop gains, means L1 plus L2 plus L3 plus L4 plus L5. 5 such loops you have already identified. So 1 minus sum of individual loop gains. Once you have used minus here, then plus. Now, pair of non-touch loops. Pair of non-touch loops, product, means we have already seen here L1 times L4 here, this one and this one, product, L1 into L4, and next L2 into L4. This is another pair, I can say. So, product of pair of non-touch loops, L1, L4 and L2, L4. Next, it is continued like this, minus if any 3 such non-touch loops, then you need to enter. However, in this example, it is not there. So, there are no 3 non-touch loops which does not have common node. So, it is 0. So, this is delta. So, it is given by 1 minus, you need to represent all that gains. L1 is G2H1 plus G4H1 plus L3 G1 G2 G3 H2 plus L4 G5 H2 plus G1 G3 G4 H2. This is sum of individual loop gains. Then product plus L1 L4 means G2 H1 into G5 H2. So, G2 G5 H1 H2 plus another pair product G4 G5 H1 H2. So, this is the way you got delta. Very simple, delta k or delta 1, delta 2 and delta 3. See, once you got delta, this is, we can say 1 minus loop gains, pair of non-touch loops and all. Then what is meant by delta k? Delta k means it is same as delta. Delta k is same as delta, but not touching kth forward path. Same information of delta, but not touching the kth forward path. Same as delta, but information which is not touching kth forward path. Kth forward path, that is called delta k. Means, now let me write delta 1, because you can see in the formula P1 delta 1, P2 delta 2, P3 delta 3. So, delta 1 is 1 minus sum of the loop gains, but not touching the first forward path. What is the first forward path? You have identified that G1, G2, G3 is the first forward path. So, is there any loop which is not touching this first forward path? No. So, it is 0. And is there any pair like you have got here, but not touching the first forward path? Of course, 0, because no loop exists first of all. So, no pair obviously exists. So, 1 minus 0 plus 0 and so on. So, it is 1. Now, delta 2 is same as delta, but 1 minus loop gains which are not touching the second forward path. What is the second forward path? You can see G1, G4, G3. So, there is no loop not touching the second forward path also. So, I can write here it is 0, no loops exist which are not touching the second forward path. So, it is also 1. Next, delta 3 is 1 minus loop gains which are not touching the third forward path. What is the third forward path? This way, G5 and then going to output. So, there are loops which are not touching this third forward path. What are they? You can see that this G2H1 is one loop and G4H1 is another loop, not touching this forward path. Because if you see the path, let me write here, this G5 you got from 1, 2, then 5, 6. Very easy now to see that these loops also you can represent the path, and then what are the loops which are not touching this third forward path you should identify. So this 3, 4, 3, that is G2H1 and G4H1 also not touching the first third forward path. So I can write here the loop gains 1 minus G2H1 then plus G4H1 is the loop gains which are not touching the third forward path. So is there any pair now which has not connected, which has no connection with the third forward path? No such pair exists. So further there is no term. So you have got now delta 1 as 1, delta 2 as 1, but delta 3 there exists some function 1 minus G2H1 plus minus G4H1 minus. So you got P1, P2, P3, delta 1, delta 2, delta 3 and delta also you have got delta. So now it is a substitution of all these gains in the Mason's gain formula, 1 by delta P1 delta 1 plus P2 delta 2 plus P3 delta 3. That's all you need to do. For any given system, you need to do this much exercise and find out the overall transfer function using Mason's gain formula. So look at this block diagram. It consists of several blocks and summing points and takeoff points. Such a problem, if given, suppose you are asked to find out the transfer function C by R. Using block diagram reduction rules, you can anyway apply and you can identify what are the forward paths. So you can apply the rule. Eliminate the feedback loop, you can apply the rule. Cascading, you can apply the rule, and finally all such. But you need to draw this block diagram when you are reducing one rule after one rule. Probably you may have to draw this diagram 4 to 5 times, and finally you will get a single block whose transfer function, overall transfer function, can be represented in the block. Now you can use signal flow graph technique by converting this block diagram into signal flow graph and apply Mason's gain formula. That will be the easy way to find out the overall transfer function. So how to draw signal flow graph for given block diagram? Now for that, you identify input as a node, you represent it as a 1, node 1. Every summing point is also one node you consider, and summing point here 3. Takeoff point also you consider as a node 4, and there is a summing point here 5. There is a takeoff point 6 and output variable as 7. So represent summing points, takeoff points and input and output as nodes. Now represent here, start with 1, 2, 3, 4, 5, 6, 7. All the nodes are represented. Now join them. Now between 1 and 2 there is no block, so it is a connection, but no block is there, represent its gain as 1 only. Between 2 and 3 you can see that there is a block whose gain is given as G1. So between 2 and 3 there is a block whose gain is given by G1. Now between 3 and 4 there is a block again G2, represent on the top of the arrow gain of that particular branch. Between 4 and 5 there are 3 parallel paths. So one is G4, so we represent that G4, and there is another path via G3 connecting 4 and 5, and via 1 there is another connection. So this way you need to draw the signal flow graph for the given block diagram. Between 5 and 6 there is no block, so represent its gain as 1. Between 6 and 7 it is again 1. So this is C output node, this is R input node. See the feedback elements also connecting from 4 to 3 with gain H2 multiplied by minus here. So minus H2, and there is another feedback from 6, it is joining 2. So 6 is connected to 2 via H1 with minus sign. So 6 connected to 2 with minus H1. So now the signal flow graph is drawn for the given block diagram. Now as usual it is the turn for us to identify how many forward paths, how many loops, how many pairs of non-touch loops you need to identify. So once signal flow graph is drawn, you can see that this is simple compared to this one, because no blocks, no summing points, etc. It is only a line and then nodes. So our aim is now to see how many forward paths exist. So as I indicated, forward path is the path connecting input and output node. So first forward path you can actually represent here 1, 2, 3, 4, 5, 6, 7. It is a path, and what is its gain? G1, G2, G4 and 1 into 1. So G1, G2, G4, gain of one forward path. There is another forward path that exists. It goes via G1, G2, via G3 to the output. So second forward path gain is G1, G2, G3, and there is a third forward path also connecting input and output via 1, 2, G1, G2 and via 1 it goes this way. So P3 is G1, G2. It goes via 1 and then finally to the output. So 3 forward paths exist in this particular example. Now let us identify how many loops exist. So the number of loops and the respective gain, you can see that 3, 4, 3 is one loop path, and the gain of that particular loop is minus G2 H2. Now there is another loop, you can see it starts from 2, 3, 4, 5, 6 and comes back to H1. So L2 is G1, G2, G4 H1 with minus sign because H1 is negative. Now you can see another loop that G1, G2, G3, then H1. So L3 is with again minus sign G1, G2, G3, H1. And you can identify another loop that is G1, G2, then via 1 this back to minus H1. So this is also another loop that exists in this particular diagram. So that is L4 is G1, G2, 1, H1. So minus G1, G2, H1. So this is the way you should identify the number of loops that exist in the given signal flow graph. Then next, is there any pair? Is there any pair of non-touch loops that exist in the system? So you can see that this is one loop you have already seen, and this is second loop, third loop, then this is the fourth loop. So no pair exists, no non-touch loops pair that exist here. So we can ignore that term. Now you need to find the transfer function C by R using Masson's gain formula, that is 1 by delta into, so there are three forward paths. I must write here P1 delta 1 plus P2 delta 2 plus P3 delta 3 is the formula. So P1, P2, P3 already identified. Now what is delta? Delta is 1 minus the loop gains already identified here. So L1 plus L2 plus L3 plus L4 plus no pair of loops exist, so 0. Now what is delta 1? Delta 1 is 1 minus loop gains which are not touching the first forward path. So first forward path is this, and there is no loop which is not touching the first forward path. So 1 minus 0, fortunately. So it is 1. Similarly, delta 2 also 1 minus. Are there any loops which are not touching the second forward path G1, G2, G3? So no loops exist, 1, and similarly delta 3 also 1 minus 0 equal to 1. So now it is only a substitution. You got delta, delta 1, delta 2, delta 3, and substitute here in the overall transfer function. It is nothing but a Masson's gain formula, so that you can find out overall transfer function. So you are not using block diagram reduction rules, and it is not laborious, it is not complex, it is only an observation by you. Observe this diagram and identify what are required, substitute them in Masson's gain formula and get the overall gain of the system. That is the beauty of signal flow graph. In the next section, we actually discuss some problems that are given in previous GATE exam. For a given block diagram, convert that into signal flow graph and find out the transfer function. And also, when electrical system is given in terms of electrical circuit, then how to draw signal flow graph for that and finding a transfer function. So any complex problem, whether it is electrical circuit or block diagram description, can be transformed into signal flow graph, and we can apply easily the Masson's gain formula to find out the overall gain.